Hello everyone, welcome to my YouTube channel MechE-FUNdaMENTALs. In this video, I will discuss about the tensile test. In the series of Fundamental of Mechanical Engineering, the topic is tensile test, in which I discuss the universal testing machine in which this test is performed, procedure for tensile test, and the stress strain diagram which is experimentally investigated in universal testing machine. Now the first one, that is a tensile test. In a tensile test, a standardized specimen is loaded under uniaxial tensile force until it breaks. The force is recorded as a function of elongation. You see, this is the specimen or the sample, and a uniaxial tensile force P that will applied until it breaks, and in this we record the force as a function of elongation, or we can say that is a stress which is a function of strain. In this test, it is determined which load a material can withstand until it begins to deform plastically, which is known as yield strength, or under which maximum load the material breaks, which is known as the tensile strength. The tensile test can also be used to determine the elongation at break, which is known as the fracture strain, in order to obtain information about the toughness of the material. So, in strength of material, the tensile test is one of the important tests which is used to determine the yield strength of any material, tensile strength of any material, and also we can measure the toughness of the material. And now the universal testing machine. This is the machine in which we perform this tensile test. Okay, you see, this is the diagram of the universal testing machine. In this, we have the two main units. The first one, that is the loading unit. You see the left one, this is the loading unit. And in this loading unit, actually, we have to load the specimen or the sample. The second unit, that is the control panel. And the load application is performed by the action of hydraulic pressure, because the load is very heavy, and the hydraulic pressure actually we use to give that particular load. And a pendulum dynamometer, you see this is the pendulum dynamometer, is fitted to measure and indicate the force coming on the specimen. So in this loading unit, we load the specimen in between these two particular heads, and through the control panel we apply the hydraulic pressure. And this is the machine named universal testing machine, in which we are doing this tensile test. Now the procedure for tensile test. The first one, that is the preparation of a specimen. Initially, the steel rod specimen is cleaned and gauge length is marked on it. So this is the shape of the specimen. You see the circular cross section. We mark two lines, and the distance between these two lines, that is known as the gauge length. So that is the length under observation. Then placing the specimen, you see this is the universal testing machine loading unit. Now this is the specimen which is held under these two particular heads. So the specimen firmly fits to the top base by operating the handle. Lift the lower cross head chuck up and grip firmly the lower part of the specimen. And once the specimen is placed, the jaws are locked. So these are the two handles. And finally, when the specimen is in between these two crossheads, then with the help of the handle we lock it. Okay, then we have to place an extensometer. Extensometer is actually to measure the elongation with respect to the load. And the last, that is the load application. So with the help of the hydraulic pressure, we are giving the load in that specimen. It means we have to apply the uniaxial tensile force, and with the help of this pendulum dynamometer we can record the applied load also. Now the stress strain diagram. So finally, when we applied the load in the specimen and we achieve a stress strain diagram, and that is the experimental investigation, because that graph is plotted in that machine itself. And here the material which is under consideration, that is the mild steel, and it is a ductile material. And the result of a tensile test is always a stress strain curve or the stress strain diagram, showing the specimen strain elongation on the horizontal axis. So in the horizontal axis we have the strain, and the stress, which is the measure of the applied force on the vertical axis. So in the vertical axis we have the stress. Okay, so as we know that in the x-axis we plot the independent variable, and in the y-axis we plot the variable, and here this stress is a function of strain, y is a function of x. So y means that the stress that will depend on strain. Okay, so strain is the independent variable and stress is a dependent variable. So that is the reason why the strain is on the x-axis and the stress is on the y-axis. And this is the graph we experimentally achieved in that universal testing machine. So now we have to explain, or I have to explain, this tensile test or the stress strain diagram in coming slides. Now the first one. Now I start that graph from this particular point, that is O, and the O means there is no stress, no strain, means the applied load is 0, so we are not getting any deformation. So that is the point O. Now you see, when we get this particular graph from that machine, so now we have to talk about its various salient points. So now the first one, that is the proportional limit, that is from O to A. Now you see, we are moving from O to A. So this is O. Now we are moving from O to A. Now what is the observation? From O to A, you see we have a line. It means the stress is proportional to strain. Okay, and it means the Hooke's law obeyed. And after A up to B, we have the elastic limit. From A to B, still we have the elastic limit. Now I conclude like that. We start the loading from O, and now we are moving from O to A, then A to B. So we can say that B is the elastic limit. This B is the elastic limit. Now what is the meaning of the elastic limit? It means up to point B, it means the load when we have up at that particular point B, if we release the load, then we will regain its shape and size. It means this is the loading direction. Let us suppose this is the loading direction from O to B, and when you release the load at B, so definitely this is the unloading curve. This is the unloading curve, and again we are up to point O. It means up to B, if you release the load, then will regain its shape and size. It means we have the property of the elasticity in the material that will remains in the body up to B. So B is known as the elastic limit. And in this elastic limit, from O to A, you see this region from O to A, that is the linear elastic behavior. Linear elastic behavior means the stress is proportional to strain. Okay, and from A to B, elastic property still remains in the body, but from A to B we have the non-linear elastic behavior. So finally we can say that the elastic property remains in the body up to B. So B is the elastic limit, and in this elastic deformation we have the linear elastic behavior up to A, means the stress is proportional to strain up to A. So A is known as the proportional limit and B is known as the elastic limit. Okay. Now what happens in the elastic deformation? Now we will see with the help of this particular diagram. So elastic deformation occurs due to the stretching or compression of the metallic bonds, which can be modeled as springs that store release energy as they are deformed and relaxed. You see, these are the atomic bonds, and we can model these bonds in the form of the spring. So when we are applying the uniaxial tension, and here we are talking about the elastic deformation, then what happens? You see, these bonds are stressed. They do not break. They are stressed actually. Okay. So it means when we apply the load, the bond stretch. It means they absorb some energy, and when we release the load, and they again recover back by that particular energy. So that is the Hooke's law, we can say. So that is the case in the elastic deformation. So we have the stretching of the atomic bonds in elastic deformation. The bond will not break up to the elastic limit, so they will recover back after the release of the load. Now the plastic region. So it means now we have to talk about beyond B. So if we load further, it means now the elastic limit cross. Now we are going in the region of the plastic deformation, which is also known as the permanent deformation. It means when we move beyond B and now we have to unload or we have to release the load, then the unloading curve will be like this. So this is the loading curve and this is the unloading curve. And now you see, now finally after relieving the load, we are getting some permanent set of the deformation. You see, up to B, if you release the load, then we come at O. But after B, because now we are in the region of the plastic deformation or this is the unloading curve, so definitely a permanent set of the deformation remains in the body. So that is known as a plastic deformation. Okay. Now what happens in the plastic deformation actually? So plastic deformation occurs when the material atomic bond are broken and reformed in new configuration, leading to permanent change in the material shape. This process involves the movement of dislocations that allow the atom to slide past each other more easily. You see, this is the diagram. So these are the slip planes where these are the slip planes where the material bond will break. And when they break, it means now this is the condition of the plastic deformation. And we get the dislocations in this slip plane actually. And when we apply load further, so this dislocation also move. It means now we are in the plastic deformation region. Now you see with the help of this diagram again, you better understand. So this is a plastic deformation caused by the movement of the dislocation. You see, this is up to the point B, up to the elastic limit. Now you cross the elastic limit. You see, this is the slip plane in the yellow region. So this is the slip plane. And you see, this is the dislocation. Now you see the metal bond breaks here and you are getting the dislocation here. Because you see now in its continuation, there is no bond. So this is the dislocation we are getting. Now further, if you apply the load, then this location will move. You see this dislocation moves like this. So this is the initial one. We are getting this dislocation of the slip plane. Then this dislocation will move like this. And this is the phenomena of the plastic deformation. Now the next region, that is C to D, which is known as the yielding. Yielding means we are getting the significant strain with very small or no change in the stress. Okay. Now why we have the yielding of the material? Now we have to understand. This yielding will start at C, so that is known as the upper yield point, and that will end at point D, which is known as the lower yield point. Okay. So at the yield point, the force required to move dislocation is less than the force required to stretch atomic bond, so dislocation move. It means the metal bond breaks, the dislocation moves, and to move the dislocation we required less force with respect to stress the metallic bond. And that is the reason why the stress is not so increased, but we have a significant amount of the elongation, and that phenomena is known as the yielding. You see, so this is the dislocation which is moving, and for that we require less force when we are comparing to stress these metallic bond, and that is the reason why we have the significant amount of the deformation without little or no increment in the stress, and that is known as the yielding phenomena. Now the next, that is the strain hardening region, that is from D to E. This is the region, this is D to E. And the strain hardening region means the strength of the material is increased with the application of load in this region, therefore more stress is required for deformation region. And this E is known as the ultimate stress point, and corresponding to that the stress is known as the ultimate stress. Now what happened in this particular region, and what is the strain hardening region? Okay, so again we have to see this particular atomic theory. So this is the edge dislocation you see here. But now we are getting the different slip planes and the different edge dislocations in that material, and these dislocation moves, and finally all the dislocation will be piled up in some region. So this is the dislocation, and here these dislocations are piled up on the grain boundaries. And now to further deformation we require more force, and that is the reason why this is known as a strain hardening, because due to the strain the hardness increases, the strength increases. So the material continues to deform past the yield point, dislocations piles up and make it harder for the material to keep deforming, and this is called strain hardening. Okay, so now we are at point E now. And now from E to F, you see this region, and this is the necking of the material. You see, this is the sample, and now you see in this EF region we have the necking of the material. It means the cross section decrease in a rapid rate, and finally at F the material will break, and that is known as the breaking point, okay? Because now the material is so weak due to that nagging phenomena or nagging formation, the material will fail at point F, and that failure is cup and cone type. So you see, this is the cup fracture surface and this is a cone fracture surface, and this is the real diagram of this cone and cup and cone phenomena, okay? And this is about the stress strain diagram. And also I will tell you the stress which we are plotting here, that is the engineering stress, because that stress is the force divided by the original cross-section area. So here at every point of the stress we are considering the initial area of that specimen, so that is known as the engineering stress. And the other stress, that is known as the true stress, in that we are taking the instantaneous area. So that is the difference between the engineering stress and the true stress. But here in this stress strain diagram, this is the classical curve, and here we are generally talking about the engineering stress, okay? So this is all about the stress strain diagram. Hope you understand this stress strain diagram. Thank you.